Recording. Cool. So thanks for bearing with me over the weekend, guys. Obviously, things got a little wild there with the move. Doing okay, though. Should be back to normal as of now. We should be kind of back to how things are supposed to be. Last week was kind of crazy, so thanks for bearing with me there. Just some notes on stuff you guys have probably already read it. Midterm and homework 3 will both be due on Friday. Midterm's out now. There were some people saying there were problems with some of the answers not showing up. I think we fixed it. It was from a problem with importing the questions from old quizzes. It didn't pull all the answers, and there's no rhyme or reason as to what got pulled. It was just kind of random stuff. It wasn't like earlier in the semester versus later, or stuff with code in it or not code. It was just completely random. So that should be corrected. Should be corrected now. If it's not, please let me know. I think I got all the questions. I had to fix them manually, so I might have missed one. If you do get a question that has answers not showing up, shoot me an email and we can fix that pretty easy. So for those of you that already tried to take the midterm, let me know if there were any problems trying to retake it after that happened, or if there are really any kind of problems with Canvas not letting you do stuff you should be able to do. Because this one was, oddly enough, a Canvas bug. Usually Canvas is pretty good. What's next? Yeah, homework. Because we didn't get the test cases out as quick as I would have liked, that'll be due on Friday as well. Homework 4 will probably go out tomorrow. So there will be some overlap there, but it won't be due for a week or so. So trying to keep the pace there. Yeah, so for those of you that wanted the test cases, you have those now. That is in a separate file on Canvas. It should be right underneath the homework entry. It's not in the homework entry, if that makes sense. So yeah, don't click where you would like add the submission, basically. Yeah, and daily quizzes are back. Today's is already up, I believe. If not, somebody say something, but should be up. We have a lot to cover, so I'm not going to waste a ton of time rambling. Does anyone else have any questions before we get jumping into stuff? I know I said I'd find a video on currying last week. That should be sometime tomorrow. I find that for real this time. Obviously, got a little busy over the weekend. So, yeah, any other questions, though, before we get rolling? Thanks for the well wishes from chat. I appreciate that a lot. Yeah, doing okay, for those of you wondering. My blood sugar got a little too low during the move, finishing up my moving stuff on Saturday. And it was good some buddies were around and kind of take care of me, but it was a little out of the ordinary. So thanks for bearing with me. Appreciate you a lot. So yeah, any other questions before we get rolling? Cool. Please let me know if there are any problems with the midterm. If there are, that is actually worth an email. You don't have to post that on Piazza. Email me if there's a problem with the midterm. I'll get to that quicker. So, oh yeah, Linnea, good question. So Linnea is asking, is the midterm timed? No, it should not be. If it is, please let me know. When I was fixing stuff, I don't think I clicked on anything wrong, but it's really easy to accidentally click a box on Canvas. So it should not be. You have as long as you need to take it. I don't believe you'll only be allowed one submission, but you should be able to like save the answers and come back to it. If that's not the case, let me know. And I'll figure out how to make that happen. So cool. Yeah, if there are any other questions about the midterm, feel free to throw those in chat and I can bounce back to them. But otherwise, I'm going to hop into material because we have a lot to cover today. I think it's a lot. I usually do this stuff over two lectures, but the lectures are shorter. So yeah, so there's one question on homework 3 that you guys are able to answer it. It's the interpreter question. But there's a bonus part that we haven't talked about. I think I talked about it or maybe mentioned it a little bit last week, but let's get into it. So take a look at these 3 inference rules and notice some commonalities, and that maybe we don't actually need to write 3 separate rules here. So I think last week someone asked a question about disjunction or the or. Could you use an or in an inference rule? And we don't really like ors, but we do let you use kind of set theory operators. That's allowed. And so here we have this situation where we have three different constructors. We have, we decide this color works okay? Yeah. We have plus, multiply, and pow, and then we have an operation if everything goes to plan. And that's basically the only difference. Otherwise, we're just evaluating the sub-expressions. If there are no errors, then we do the operation. If there are errors, they're still handled all in the same way. So I only did the okay rules here. But if anyone would have thrown an error, they all handle errors in the same exact manner. Okay, they don't have any different errors. So there's a reason I didn't include subtraction here, for instance, because you could go negative or division, where you could have a division by 0. But they all have exactly the same behavior. All they do is they take a different operation and execute it on two expressions. Can we write a single inference rule that captures this behavior in a single rule as opposed to 3? We're lazy computer scientists. We want to do this all in one definition. And Kate, to address your point, some are still showing up as blank. Can you send me the actual question in an email, like copy and paste the whole thing, and I'll take a look at it. Thank you for that. Yeah, so we can write these inference rules, a single inference rule here. You know, draw our big line. And here we can do something like C with E1, E2, where C is going to be a variable this time for our constructor name. And then what I'll do, I'll copy to save myself some writing time. The top line will stay mostly the same. So we have, you know, E1 and E2 evaluating down to number values. But then what do we get on bottom, right? So we're going to end up getting a num_val. But then what goes inside these parentheses? What do we do? How do we figure out what C is supposed to be doing? So here we add one more premise above the line, and then we say C is in the set plus mult and pow. So here we're saying that it's one of these. It's either plus, it's either mult, or it's either pow. And then now what goes inside the parentheses? Well, we need to define some way of getting the operation back. So we'll say underneath the line where op C, or rather op of, let's say, plus is equal to plus op of mult equals mult, throw some parentheses around these, and op of pow is equal to our nice caret. And then what we put here is we put op C. So that's kind of just a placeholder function for whatever the operation is, of V1, V2. So now we've effectively written this as a single rule. There's a little bit more going on inside it, but essentially it's nice and condensed now. We're not repeating anything. So that's what we like to do in this class. Is we don't like to repeat ourselves. We like to be concise. We like to abstract where possible. Yeah, so where was I going with that? There's another follow-up there. Oh, so for the problem in the homework, what you're asked to do is basically write this inference rule as a function. So write that in the error handling cases as a function. It's going to be a function that looks something like, I think we call it eval bin. We call it eval bin. I don't think we do. We definitely do. We call it eval bin. It's obviously it's an evaluation function. So it's producing some value at the end. And then because it's an evaluation function, I think this is on just arithmetic. So we're not introducing variables yet. That's homework 4. We give it an expression, or actually rather 2 expressions. But then we also have to give it the operation. How can I give eval bin an operation to do? Any ideas? It's a function, right? So what type of that function for this one is it going to be? Yeah, but what is it as a function, kind of in the Scala level? Here. It's going to be just nat to nat to nat, right? So it's a binary operation on natural numbers. And I'll talk a little bit more about this in a second. Or I guess integers, if we're using integers, whatever our number thing is. You could do this for anything. You do this for Booleans as well. But that's the type of the thing you're looking for. So there's some bonus points in it for you if you write your interpreter in this style, using basically this as a helper function. It makes things really nice, kind of concise and small. Why are we able to do this here? Any ideas why are we allowed to do this in this situation? Could I have done this if, say, I had another operation that took 3 numbers and produced a number? Would it work, really? Not really. The answer is no, not really. Could I do it if my things were all different types? Not really. They all have to, the functions at least all have to have the same type. So nat to nat to nat. They could be something else, surely, but they couldn't be like, I couldn't combine a nat to nat to nat rule with a bool to bool to bool rule, right? That wouldn't be okay. Yeah, so that's where we get into some trouble, because what we're doing here is we're evaluating expressions. We have to kind of have some way of tying the expression to a type, which you can't do if you just do A to A to A, because here you wouldn't have anything to say, oh, well, E1's a num val. Now you could kind of go another step, but the rules get really gross at that point. You don't want to do that. This is kind of enough. This is about as much kind of extra baking in of kind of syntactic sugar that we do in these rules. Otherwise they get really big and you just don't, defeats the whole purpose. Inference rules are supposed to be a really quick read, give you an idea what's going on. So good question. Yeah, so we can do this here because it's a binary operation. They all have the same type. It's a consistent type for the operation, which and they have a similar evaluation. They all evaluate in the same way. They handle errors in the same way. So we can kind of wrap them up into one nice eval bin. So yeah, so similar behavior. Same type of operation. I'm writing this down for a good reason if you guys want a little hint on what's on the quiz today. So cool. Sweet. Any questions about eval bin or that bonus problem? I don't want to spend too much time on it because it's actually not the main topic for today. Feeling good? Cool. So let's move on. And if folks in chat, if you need a second to type, that's okay. I'll be writing a header for a second. Top of the next page, we're going to start introducing functions in the lattice. We may not quite get to the full semantics today, but we will at least get to like the expressions, how it behaves, what kind of values do functions produce, things like that. Yeah, so let's start with just a really small example of a function in Lattice, just to see the syntax, the concrete syntax of how it will behave. So here we have a function. Let square equal function on x will be equal to x times x in square 10. Hope the syntax isn't too offensive to anyone. I think it's a fairly straightforward thing. What would we expect this to produce? Should be a fairly 100, right? Just a squaring function. So say this evaluates to 100, or maybe if we're being really pedantic, numval 100, something like that. Nice, perfect. I like it. Guess this is really just to get us familiar with the syntax. Note that we still use a let binding right there. We're just using a let expression. We still give a variable and a name, right? And we still have the in part. So this part is all actually a regular old let expression, okay? Actually, I'll do that in a different color so we can kind of keep track of that. And then it's this part that's the actual function def. Okay, so we can still separate these 8 function definitions. Will almost always occur inside of a let expression. So we're going to be reusing a lot here. We're not having to define some new binding syntax for the name. We're actually going to be able to just reuse the let bindings from last week, which is kind of cool. Cool, no questions in chat yet. What is the scope of the function defined in this way? So that's a good question. Let me pull out that example. Just let me find that example because I've got 4 here. Yeah, so we'll enter the scopes question in 2 examples because I want to do this other one first, I think. So we'll come back to that. Remind me to answer that question if I don't do it myself. So another example. Let's say let x equal 10 in let y equal 15 in let sq1 equal function x function y in x plus, or sorry, definition x plus y times y in square 1 x y. Yeah, it's a long one, right? What would we expect out of this problem? And every semester I write this example, I kick myself for using 10 and 15 because it makes actually figuring the numbers out not so easy. I ought to know. Is it 235? Sounds right. It's a weird number. X plus 15 times 15 is what, 225? Plus 10. Yeah, 235. You got it. Cool. So 235. I like it. Now, why didn't you do, well, I guess it really doesn't show here, does it? So this example is really just showing if I need multiple arguments to a function, I just rewrite the whole kind of function thing again. Does anyone remember what this is called? I talked about it, I think it was last week, or maybe it was the week before. The C word. It's also a tasty food. Yeah, it's currying, right? Right on. So that's what this is doing. We don't need to define anything like a product here, which would also be really awkward because we'd have to define polymorphism to do that, right? If we wanted to define a product type. Here, we just get that through currying. So using currying again here. Anything else to point out? Yeah, and then note that using X and Y, they're kind of, this is also bringing in scope a little bit. It's not binding the X and Y inside the function to be X and Y. I could flip the X and Y, right? And it would still give me a different answer, right? As one would expect with a function. So let me take a look at example 3, because this one's really long and I don't really like it. Yeah, so does that answer any scoping questions, or can we think for steel beams, whoever was asking about scope, elaborate on your question? Because I should note that the scope of these functions is going to be the scope of whatever the let binding would allow you to kind of refer to, right? Where if you have kind of a shadowed variable, say here with X and Y, it's going to refer to the variable in the function. So that's this one. I'll use a different color here. So this refers to up here, initially, right, with the function definition. And the Y here refers to the Y. That's because it's the most recent Y, right? So very similar to our let bindings from last week, or really the same if we think about it. Let's see. We won't be able to define recursive functions yet. And I'll show why later. We'll actually get back to that example. Because that's really because of our implementation. We'll get in trouble for doing recursion. So yeah, let's talk about the syntax of these. So this is kind of introducing the concrete syntax a little bit. Let's try and define some abstract syntax for this. So okay, so we're just going to be extending our expression language again. So we have expressions, definition. I'll throw some dots in here. We have other definitions we've done. There are other constructors we've used up to now. So, it includes your plus, your multiply, variables, let bindings, all that's still here. And then what do we need for function definitions and function calls? What should we add to our language? A lot of people are catching up on writing. So any ideas on what we should add here? So what's our new syntax? What's the new concrete syntax we introduced? If we go up to the examples, what didn't we have before in these examples? Yeah, so the function keyword, right? What is that part of? What could we call that? Like this guy right there, or say up here. There's a big hint in white right there. It's a function def, right? So let's call that, give it a constructor. Let's call it fundef. And what should fundef take as arguments? Let's look up here. What else could it take? I'm just giving it a name so far, nothing else. For sure, an expression, right? Which one are you looking at? Or what are you looking at? Which part of right here is an expression? What is that an expression though? Think about that a little harder. It's taking in an x, but could I put, say, if I had an expression here, could I give it, say, in a definition, would it be valid to write something like function true? No, right? That doesn't make sense. So what should I use there? Because it's really not an expression; it's a name, not a vowel. It's a name, right? What do we use? What's our type for names? Think back to our let bindings last week. These strings, right? So for that first argument, we'll just have a string. And that'll be the name of the variable we're giving it. Now, what else should we throw in our definition? Well, we have that x times x part. That's the expression bit. There you can see you're getting a little ahead of yourself. You're right. There's an expression there. It's just a little farther down. So I have a string and an expression. Cool. Yeah, so here, if we took this example, this might become something like fundef x, and then we're expecting an expression, so we have mult var x var x, like so. I might be missing a parenthesis, but something like that. Cool. How about function calls? That's the other thing we're missing. So something like here, that square 10. What do we need to represent this as far as our abstract syntax goes? What could we do with that? We can start by giving the constructor a name, per usual. We'll call this one fun call for function calls. Now, what should a function call take? So if we look here at square 10, what's the second argument going to be? That one seems pretty straightforward. What is that? The 10 part. Well, it's whatever type it's looking for. You're actually answering a deeper question here. What, in terms of our kind of language of languages, what ought that be? Not a vowel quite. It will eventually be a vowel, but not yet. Because I also could put something like 10 times 10 there. That would be valid. So an expression, right? That's what the little e is. So this is an expression. Okay, so I could put an expression. That's definitely the second argument. Now, what about the first part? How do I refer to the function? The square bit. I need to name it somehow. Should I put a string there? That's a good starting point. I could put a string there. That would be okay. Now, if you're writing in pen, don't write this down yet. Okay. But I'd actually posit we could do something else. What if I wanted to say, write this function? So I could write function x x times x, 10. Immediately apply it, right? So I could put parentheses around here, I guess. Immediately apply the function, right? I'm not giving it a name. Like this isn't a string. So what else could I put here instead of just string? Fundef, but what is a fundef? Right? Because fundef isn't a type, it's just a constructor. Another expression, right? Right on. So we do two expressions for function calls. Now, if I wanted to write square 10, how could I write that? So obviously a fun call. But then what goes there? No, just for this one, for the square bit. It wouldn't be 10 times 10 because you're worrying about evaluation right now. Not x times x, because this is just a name. This is the actual concrete syntax I'm writing there. I'm going to put a var square. So function names are just variables like everything else. So again, this is us reusing everything we can with our let bindings to start using functions. So hypothetically, earlier in the program, I've defined square. I've given it a name. It's a variable just like everything else in my scope. And then I can also give it, you know, num 10. And that's the expression num 10, not num val, because remember, num val is the value we get from evaluating that. Cool. Is everyone with me so far? Graham, I was just a little late seeing your answer. Say a function name and a list of arguments. That's okay, but we're going to do currying. So I actually do like that, Graham, as far as like if we wanted to make a scalable language instead of doing, say, a function name and a list of variables. So I think that's for fun call. Hypothetically, you do a list of expressions, you know, provide multiple arguments. That's nice, what we call syntactic sugar. Usually at like your machine code level, you don't implement it that way. You usually use currying, but kind of at the programmer level where you want it to be nice and ergonomic, you would do something like that. Let's see. Okay, so
function definitions, something that's going to be stored in the environment.
Oh, I love where you're going with that. Yes, so the function definitions are going to be stored in the environment, but how? Because what gets stored in the environment?
Typically variable names.
Variable names along with
their values.
Their values, right? Is fundef and funcall, neither of those are values, right? Those are expressions. So here our question is, what is the value of a fundef? Yeah, so this is a pretty core question because there's a lot that goes on with function definitions, right? Because there's some scoping stuff happening whenever you have a function. You have to keep track of another variable name in addition to itself. There's a little bit more going on here. And so for instance, in this, I'm trying to think of that example now. Up here, we know that this x refers to that x, this y refers to this y, not some other x and y. How do we capture that? What happens if I have something like, yeah, here's the example. So like let f equal function x plus x, let x equal 5 in f of 10. How do we keep these x's from becoming that x? This is an interesting problem, right? So we need to somehow keep the scope of f with f. We need to kind of roll the scope up with f. So this is where we introduce something called a closure. And closures are going to be the values of function definitions. So it being a value, naturally, we're going to extend that type we had before for value. So val or value is defined to be, we have other stuff, so we'll throw some ellipses there. And then we'll call these closures. What will a closure take? Okay, well, a closure will take, and this is going to be a really handy acronym if you guys remember what closures have. P. Remember P. Kind of silly. Remember P. So it takes the first P, which is the parameter. The parameter is in the form of a string, right? That variable name that you're binding. It then takes an expression. Which is the body of the function. And lastly, it takes an environment, which is that sigma we defined last week. That could be in the form of a dictionary. Typically, it'll be, the type will be dictionary. So it's funny, a few years ago, I came up with this acronym. I was just teaching this lecture on the spot. And I'm like, okay, well, you guys remember it's like a string, an expression, and an environment, and like a parameter, an expression, environment. I'm like, I just chuckled to myself, and everyone's like, why is this guy laughing to himself? Is he losing it? Which isn't uncommon for academics, right? And so I'm like, it's P. And it took everyone a second, and finally they're like, oh, no one ever forgot it the rest of the class. That question on the final got like a 95% hit rate or something. So I hope that helps you guys remember this acronym. We'll use closures a lot the rest of the semester, at least in this way. There's a couple other types of closures we'll play with later as well. Yeah, so the idea is that it takes that parameter and the expression of its body, it wraps those up, right? That's just the function definition part. So it's basically taking the function definition as it stands, rolls those together with the environment at time of definition. So let's add a little note on the side about that. Environment at time of function definition. And this is to solve that problem we showed just a second ago, here where I have let f equal function x. I have x plus x, and then I define x, but it's a different x. It's not the same x. So what happens when I evaluate this is I go find f's closure. I pull apart, okay, find this string, this expression, right? But then when this string is going to write over this dictionary. Okay, but this dictionary won't have this x in it. Right, so there's no chance you might accidentally get those mixed up. It doesn't quite pop out in this example, and I'm a little embarrassed now that it doesn't. But it's easy to come up with examples where it would, where you would have some kind of shadowing going on, where it's like, okay, well, I defined over a variable in a function, I didn't mean to do that. That's why we roll up these closures as we go. Yeah, so actually, here's the example where it does. So it's where you have something like let f equal function x plus x, then wait, is that it? No, it's where we would have something ahead of it as well. So like let x equal, actually we'll call it y now, y equal 5, for instance, and let x plus y, where this y is referring to the 5 up here. And then we let y equal, say, 10 down here in f of 2. This results in, okay, well, we plug 2 in for x, and then we have this y is a 5. So we get 7. Not 12. Cool. That's why we have the closure, is it says, okay, well, look up to what the environment was when I was defined. Well, and that's essentially what a closure is really good at. It captures that kind of state of the world when it was defined, because you don't want it kind of crisscrossing variables willy-nilly, especially when you might have busy kind of scopes and reusing names all the time. You don't want that. So that would be a behavior we wouldn't really expect. That's what closures help us deal with. So let's see, we're actually going a little faster than I was even thinking. Any questions, especially online, because you guys probably haven't had time to type. I've been moving kind of quickly. Any questions so far about this, where we're going with this? Any clarification? I'm not seeing anything. Cool. Let's see. Yeah, so let's look at a particular example, and let's look at what value we get out of a certain function definition. So let's assume the environment sigma is just equal to x maps to 5. Evaluate function of x. Oh, no, sorry, function of y. Forgive me, those of you writing in pen. X plus y times y. So it was that example from before. What does this look like as a closure? That's my question for you. I'll give you guys a second to try that out. Should just be about one line of writing, not even a whole line. Got any ideas? What are we doing?
So closure, and then like the 3 things you put in. First one would be y.
Okay, so we have closure of y. comma,
and x plus y times y.
x plus y times y. And in reality, that would be the abstract syntax. I'm writing shorthand here. So it'd really say plus x mult yy, right?
And just x maps to 5.
Okay, and then the x maps to 5, right on. So a pretty straightforward, not y, x maps to 5. Pretty straightforward interpretation. It's not really all that complicated. It's just necessary as a mechanism for doing our evaluations, right? How might we expect this to work if, say, I gave a variable to a function? So say, or actually rather, how does this work when I do a function call? Actually, I think that's the next question really to answer. Is say I have a function call for, how do we evaluate? And let's say we gave this a name, right, in the environment. Say f maps to, you know, and it's in the environment now. How do we evaluate f of 2? How do we handle that? And try and do it out in steps if you could, because there's a couple steps that happen here. So we can start somewhere pretty straightforwardly, right? We're going to start by going and looking, let's go find f. Okay. So we found f, it's this closure right there. We're going to bind the argument, whatever that is, to y. Okay. We're going to add it to the environment, right? So now we take that x maps to 5, and we're going to slap, you know, y maps to 2 into that environment. Okay, call it sigma prime. Now evaluate x plus y times y. That's a much easier problem, right? How do I do that? Well, I take the 5, plug it in, take the 2, plug in, and I get 9, right? Look good? Now, what happens if I do, say, how about f of 3 plus 2? Somebody walk me through how that would happen. See that common?
Yeah, probably sort of the same way, but y just maps to now an expression.
Is it allowed to map to an expression though?
But we have to evaluate that.
Oh, so we could evaluate that 3 plus 2, right? Okay. What does that evaluate to? Yeah, so now I have x still mapping to 5, right? Or num val 5, right? We're using shorthand here still. And y maps to 5, right? Y doesn't map to an expression, it maps the value of that expression, right? Right on. And then I do, you know, x plus y times y. That should be 30. Right? Is that 30? Cool. It's a pretty satisfying function. It gives us like 9, which is a square, and 30, which is like, it's not a square, but it's a nice kind of round number. Does it always give, it does, definitely doesn't always give you really nice numbers. If you did like an odd, does it?
63 times, like 7 times.
63. Oh, and even if you did like +1.
It's like, well, 9 times 9.
No, because it's only the addition of a single number. If you did like X, if you also multiplied X by 2, it'd always be an even number. This isn't that interesting of an equation, unfortunately.
Found something cool, but
Oh, I'm sure. Don't get me wrong. There's so much cool stuff going on with this equation. You have to really reach in this class because we don't ever define like lists yet. We haven't done lists yet, right? We haven't added those to the language. So we have to reach for these like, oh, it's a cool equation for some reason. Cool. Yeah, so I like that. So basically we want to make sure that when we're kind of evaluating the value being passed to the function, we actually evaluate it. We don't just pass the expression along because it needs to eventually be added to the environment, right? We can kind of look at functions. This is just a remark. We can look at functions as delayed let bindings. What do I mean by that? I mean that, say, let X equal, 5 plus 2 in something. Let's say I didn't know what 2 was. I could change that to a variable, right? So then this expression then becomes, 5 plus X, but I need a function there, right? So then I'd have let X equal function Y 5 plus Y, in ... So you can think about it as like, hey, I don't have all my information yet. I can't quite compute this thing, but if you give me an X, I can, right? Or here a Y. Okay, so we can think about it in that sense. It's a delayed let binding. It lives in the same world as a let binding. It's a very similar idea, but it's saying I don't have all my information yet, but I can fill in most of the answers. Not quite all of them, most. I can get you this far with the computation, right? That might be helpful for some of you to kind of wrapping your heads around functional programming too. Like it sometimes helps to think about stuff that way. It's like, this equation works great here, not here. Why? Maybe there's a variable to kind of pull out of that, right? And this is kind of general programming stuff anyway, but just another way to think about it. What else to cover here? We still have so much time. I don't necessarily want to get into the semantics today, but we can.
I have a question about your use of function in this let binding.
Yeah.
It seems to, like, what function is it referencing? Because earlier we had in the square one function, for example, we had function X, function Y, but really we only operate on Y. We just take X as a input to that function. So I was hoping you could say a little bit more about what that function means. What function does it reference specifically, and how?
Do you mean this keyword right there?
That's right. That's right.
Yeah, so that's actually signaling a function definition, not to be confused with a function call. Does that clear that up maybe? If not, then maybe I misunderstood.
Yeah, it does. It does.
Where you're going. Okay.
What function is it referencing?
So it's not referencing, it's creating. Oh, I guess, okay, so X is the function here. Maybe that's the answer to your question.
Okay.
So it's saying X is a function defined as 5 plus Y. Right, that's another way you could read that with variable Y, right? is a function on y. I guess that's how you'd write that in English. X is a function on y defined as 5 plus y. Cool. Sweet. So that cleared that up. Any other questions from anybody? I went too fast today. I didn't want to jump into the semantics yet because that is actually a really good. So we don't quite have enough time to do it all today. Yeah, so I'm actually going to go off on a sidebar, so completely different topic here, mostly because I think it's next week's recitation talks about this a lot, proof trees. So yeah, so segue. Something like a person on a Segway. Yeah, so we'll pick that up tomorrow. I'll write that down real quick. Pick up with semantics tomorrow. For those of you that just kind of read the notes and move on, that's an important note. So let's talk about well-formedness. This is something I should have talked about last week. We didn't when we introduced let bindings. So in lettuce, as we've defined it, we run into a problem. And this example lets that problem be known. What's the problem with that expression? Yeah.
So like why is not defined?
Yeah, why it's not defined, right? We kind of talked about this a little bit. It's an error case, certainly. So why is undefined? And when we have undefined variables in an expression, we actually have a name for that. We call this, or we say this expression is not well formed. And that's the word we're looking at, well formed. So I guess actually that should be in white if I'm staying consistent. Cool. So what is well formedness? It means we only use variables which have been defined. Now, I'm going to pose a question. Can we tell if an expression is well formed without running it? Aaron says yes. That's a quick nod.
If you're assigning a variable to a value that doesn't exist in the environment, you can kind of just read the syntax.
Yeah, you can usually just read the syntax. You don't have to compute the whole program, right? So it kind of follows just from like our experience programming. We already know. And it's often the case. You can look at a program, just glance at it and say, hey, silly CS 1000 programmer, you didn't define this variable, right? And we've all been there. We've all done that. The sign of becoming a better programmer is usually, hopefully, not doing that as often. You still do it all the time. I do it all the time. Yeah, so the answer to that question is an unequivocal yes. Just glance at the program. But could we kind of formalize that kind of just glance at the program process? Could we turn this maybe into a set of inference rules on our expressions? How might we do that? Let's just pick an expression at random. Let's do one. Try and define well-formedness. And also note, we're going to introduce a little bit of notation. I'll write well-formed as WF. How about for like num? So let's say, let's write an inference rule for it. We'll write WF num n. What needs to be true for this to be true? Could num n have any variables inside it? So it must be well formed, right? Yeah. This isn't quite the definition. We're going to throw an S on there. That S is going to be the context that we're in. It's kind of similar to our environment, but it's just a list of the variables we've defined so far. Not sure why we use S in my notes here. Often it'll be some other Greek letter. So what if I wanted to do this for something like, let's say, what's well-formedness for, say, a variable? So var x under S. What needs to be true for this to be well-formed? Well, we're not evaluating anything, remember? So remember, X is a string. Needs to be defined. Yeah, where could I look for it to be defined though? Do we have a place where we're keeping track of all the variables we can use? That's S, right? So I can just say, you know, if X is in S, then our variables are well formed, right? You know, we can give these rules names too. We should actually, because on Monday you'll be using these. So you could call this one, say, WF num, WF var. How do I add variables to S though? Because right now we're not actually adding anything to S. What expression might add something to S? A let binding? Yeah, sure. Yeah, so you could have, say, well-formed, what's a well-formed let binding? So let takes a variable name, let's just call it X here. It takes an expression for the body and it takes an expression for the rest of the program. We'll call it EP. And it's well-formed under S when what? What needs to be true here? Do we need to say anything about this X at all? Not yet, not really. How about EB? Yeah. Or is also, well, EB doesn't need to be, but it needs to be what? Because it might not be a variable, it's an expression. It must also be well formed, right? Yeah. So as long as WF of EB, but is it under S? What does S need in addition? If I have a let binding, EB is allowed to refer to something from that let binding. What is it? the body of my function is allowed to refer to a variable, right? That variable is x. So if I had var x inside of there, that would be okay. So I need to do s union x, add x onto that. Cool. Close out that well formed. So that has to be well formed under s with x, right? Because we can have that x inside. And then how about EP? Does EP have to have anything be true? It's another expression. It ought to be well formed, right? Yeah. Okay, sort of the same thing. EP, comma. Do I use S union X or just S? Why? Okay, so here's my question. So would this be well formed? Would function, sorry. Oh, I've just made an error as we've been doing this. We goofed that up. We said function. This is a let binding, not a function def. Oops. So let's roll back for a second. We shouldn't have the union right there. Yeah, me too. See, that's what you can run into trouble there. It's really subtle, right? So EP should have S union X, but EB should not. That is my bad. Wow, you guys caught me out there. I had us convinced. Cool. So that's what we're looking for that well-formed definition. I think we'll hold off on function for now. Yeah, because I don't have that one in front of me and I don't want to accidentally write it wrong. But function is a little bit more complicated, right? Because you're adding a variable to your well-formedness kind of stack. And at the same time, you have to handle that closure. So like that handles a little differently, right? I think we do see that on Monday. I think there's a rule for that on the kind of worksheet we'll give you. Yeah, so well-formedness, it's not any different really, these rules, than say the evaluations we've been defining. It's just a different property about our language. But it's also kind of the barest form of, it's not really a type checker, but it's that in that class of things where it checks your program to make sure it works before you have to run it, right? Because you could certainly try and run these programs and they'd fail out. But they're also in this really cool class of properties where it's like, I can actually throw a program at it and say, well, this crashed because of this reason, because there's an undefined variable. And you can answer that with a well-formedness checker and say, no, it's this whole program's well-formed. Don't need to worry about calling a variable it's not defined. There's value to that. We do that with types. Types work in the exact same way. Am I using a list where there should be a number? It's a similar kind of thing. It says, check this for me before I have to run my program, because for whatever reason, I don't want it to fail at runtime, right? Which is usually true about programs anyway. You don't want them to fail at runtime. It's not permissible. Sometimes it is. Yeah, and so well-formedness gives you an avenue for that. It is also going to allow us to talk a little bit about proof trees on Monday for your next recitation. But I think that's where I'll leave you guys for the day. We got 5 minutes. I can hang out and answer if anyone has other questions. Yes, Sarah.
So why would